So we're going to start off with some matrix multiplication today. First of all, let's make sure that our dimensions work out and we know that we can multiply these two matrices. So this right here is 3 rows by 3 columns. So it is a 3 by 3. This matrix is also 3 rows by 3 columns. And the inside dimensions match. They're both 3s. And the outer dimensions tell me how large the answer is going to be. So I know that my answer should be a 3 by 3 matrix. And so far, when I've been doing this multiplication, I've been pretty slow and methodical in terms of writing out all of the pieces. I'm going to start to hit the fast forward a little bit on the matrix multiplication from here on out, but I'll do at least one of them a little bit slower. So it's a 3 by 3. So I know that I need all of these pieces to give me my 3 rows and 3 columns. And I'm just going to pick one of these. So for example, this box right here, it's in my 3rd row and my 2nd column. So this is in row 3, column 2. So to get what goes inside of this box, I know that I'm taking row 3 of the first matrix times column 2 of the second matrix. Row 3 times column 2. So got 0 times 2/3. Well, that's 0. Plus 0 times 1/3. Also 0. Plus -1 times 0. Also 0. And if you did this right, you should have gotten a bunch of zeros in your matrix. I was trying to make our lives easy. Let's go through the rest of these. So this one is in row 1, column 1. So I'm going to take row 1 of the first matrix times column 1 of the second matrix. I'll end up with 1 times 1 plus -2 times 0 plus 0 times 0. Overall, that gave me a 1. This is in row 1, column 2 of my matrix. So I need row 1 times column 2. I've got 1 times 2/3. Okay, I'm at 2/3. And I've got -2 times 1/3. Well, that's -2/3 and then 0 times 0. So I had a plus 2/3 and then a minus 2/3, giving me another 0 in our matrix. This right here, I'm in row 1, column 3. Row 1, column 3. I've got 2/3 plus a -2/3 plus 0 times -1 is 0. So conveniently, we have another 0. This is row 2, column 1. Row 2, column 1. I've got a 0. And 3 times 1/3 should be +1. And 1 times 0 is 0. So what did I get? I got a 1.
Column 1.
This is in, I know I'm doing these kind of arbitrarily, but this is row 2, column 1. So I need row 2, column 1. I've got 1 times 0, that's 0. 3 times 0, also 0. 1 times 0, real boring. Lots of 0. Here, I'm in row 3, column 1. Row 3, column 1. 1 times 0. 0 times 0, -1 times 0. Lots of 0. This is in row 2, column 3. Row 2, column 3. 0 times 2/3, I got 0. 3 times 1/3, I'm at 1. And 1 times -1 should be a -1. So that was a +1 and a -1. I've also got a 0. This last piece is in row 3, column 3. So I'll take row 3 of the first matrix times column 3 of the second matrix. 0 times 2/3, 0. 0 times 1/3, also 0. -1 times -1 gives me a +1. Bam. Okay. Now this matrix over here actually has a special name. This thing over here we refer to as the identity matrix. And we abbreviate the identity matrix. Identity matrix with a capital I. And then we usually give a subscript to say how big the matrix is. Because this is a 3 by 3 matrix, this is I3. Now, what is special about an identity matrix? So the 3 tells me that it's 3 by 3. And for an identity matrix, the primary diagonal has 1s, and there are 0s everywhere else. Now, if I wanted to talk about the identity matrix for a 2 by 2, I would show that as I with a subscript of 2, saying it's a 2 by 2 matrix. And I would have a matrix with 1s on the diagonal and 0s everywhere else. I can keep going as big as I want. I5 would mean that I had a matrix with 1s on the diagonal, 1, 2, 3, 4, 5, and 0s everywhere else, but I'm going to be lazy. And sometimes in math, we do this lazy thing and we just write a big 0 and like a ... to say, hey, the rest of this junk is all 0s. So let's talk about what that identity matrix multiplication would look like for a 2 by 2. So I'm going to pick a random 2 by 2 matrix. How about 2, 3, -1, 4. And if I were to take that matrix A and multiply it by I2, so the identity matrix for a 2 by 2 matrix, that's going to look like 1s on the diagonal and 0s everywhere else. And if we do this matrix multiplication, I claim that we are supposed to get exactly this matrix A back, because that's what it means to be the identity matrix. I'm going to do this one pretty quick. So this is going to come from row 1 times column 1. So I've got 2 times 1 plus 3 times 0. To get this, I've got -1 times 1 plus 4 times 0. To get this one, I've got 2 times 0 plus 3 times 1. And to get this last one, I'll have -1 times 0 plus 4 times 1. We did. We got the same matrix back. And that 5x is equal to 3. And I asked you to solve for x. And my guess is that y'all are going to divide by 5, which is totally fine in our algebra world. But the other option for how to get the x by itself was to multiply both sides by 1/5. And when we do that, the 1/5 times 5 turns into 1. And although we don't have a way to divide matrices, what we do have is this concept of finding something that we can multiply the matrix by that gives us back the identity. And we call that is the inverse. Algebra-wise, 1/5 is the multiplicative inverse of 5, because if I take 1/5 times 5, I get the identity back. We don't usually talk in terms of that vocabulary when we're talking about just algebra and numbers, but technically it's the same vocabulary. So let's see what that would look like for a matrix. Now I'm regretting that I erased my example problem, but you all have it on your paper. The matrix that I gave you to start with for our warm-up, I think I had in my calculator, maybe, yes. So I gave us the matrix 1, -2, 0, 0, 3, 1, 0, 0, -1. And we multiplied that by the matrix 1, 2/3, 2/3, 0, 1/3, 1/3, 0, 0, -1. And what we got back as an answer was the identity matrix. Well, what that means is that if I called this matrix A, then this matrix is A inverse. By making our generic matrix here. Oh man. Maybe I want to do it with some numbers first, and then we'll go back and talk about it with some letters. So let's say that I have the matrix 2, 3, what did I say before? -1, 4. I think that was a matrix we had a second ago. So if here's my matrix A, and I want to find A inverse, then what I'm looking for is sort of the magic combination of things to put in here so that when I do that multiplication, I get back I2, or the 2x2 identity matrix, which should have 1s on the diagonal and 0s everywhere else. Well, that looks gross. But if we do the matrix multiplication on the left-hand side, I'm going to end up with, since this is a 2x2 and another 2x2, I know my result will be a 2x2. I'm going to give myself a little bit of space here, but to do the matrix multiplication, I'll have 2 times A plus 3 times C. And then I'll have 2 times B plus 3 times D. Down here, I'll have -1 times A plus 4 times C. And over here, -1 times B plus 4 times D. And if I need that to be equal to the identity matrix, then this has essentially told us 4 equations with 4 unknowns. I'm trying to solve for the A, B, C, and D. So I'm going to set each of my equations equal to that same element in this matrix, meaning the 2A plus 3C needs to be equal to 1. And -A plus 4C have to be equal to 0. So let me start writing these out. So I've got 2A plus 3C is equal to 1, and -A plus 4C is equal to 0. If I do the same thing with these 2 equations, I'll get 2B plus 3D is equal to 0, and -B plus 4D is equal to 1. Now, even though it looks like 4 equations and 4 unknowns, it's actually 2 pairs of 2 equations and 2 unknowns. And you can solve each of these however you like. Personally, I think it's probably going to be easiest to take that bottom equation, add A to both sides, and make this instead say A is equal to 4C, which is going to let me take that and plug it in right up here. So if I do that and I take the 4C and I plug it into that top equation, I'm going to end up with 2 times 4C plus 3C is equal to 1. 8C plus 3C is equal to 1. So 11C is equal to 1, or C is equal to 1 divided by 11. Well, if C is equal to 1 divided by 11, then I also know what A is. A A must be 4 times that, or 4 divided by 11. Now let's take this pair of equations. If I take this second pair of equations, if I wanted to solve these, again, I have options. Since we did that one by substitution, I guess I'll just do this one by substitution also. I'm going to choose to avoid fractions. So I'm going to take the second equation and rewrite that by adding b to both sides and subtracting 1 from both sides. So I'm going to take that second equation and make it look like 4d minus 1 is equal to b. So that 4d minus 1, I can plug in here for b. Well, when I do that, then that top equation would turn into 2 times 4d minus 1 plus 3d is equal to 0. Get a little bit of distribution going on. 8d minus 2 is equal to 3 plus 3d is equal to 0. And I think that's going to say that 11d is equal to 2, which means that my d must be equal to 2 divided by 11. Well, if that's what d is, then we can plug that back in here to get b. Can I do that in my head? I do not trust myself to do that in my head. I'm going to write it out. So now I know that, give myself a little bit of space. B has to be equal to 4 times what we just got for D, 2 over 11, minus 1. So that's 8 over 11 minus 1. And I'm going to rewrite that 1 as 11 over 11. So that I get negative 3 over 11 for B. Man, that was a lot of work, but I promise it's worth it because we're going to have a shortcut momentarily. So if I put all of that together, then this matrix A, B, C, D looks like my A value was 4 over 11. My B value was negative 3 over 11. My C value is 1 over 11. My D value is 2 over 11. Now you might notice that all of the numbers we came up with are something divided by 11. Just for fun, let's factor it out. So if I were to pull out that 1 over 11, then what I would be left with in here would say 4, negative 3, 1, 2. Well, it turns out that if you employ some cleverness, the same pattern repeats itself every time we're finding the inverse of a 2 by 2 matrix. This part right here, you just take the numbers on the diagonal and you swap them. These numbers over here, you just take the opposite signs. And this number 11 right here is so special. We use it for so many different things. It has its own name. And that little 11 down there is the determinant of the matrix. write this in as the determinant. That's a DET for determinant. I'll write this as the determinant of A times, we swap the diagonal, and we make the other numbers negative. Now the formula for how to find the determinant, this is super critical for us in 8.6 and in 8.7. Maybe not so much in 8.8, but definitely next quarter in 17C. So the way that we would find the determinant of that matrix is minus, I like the sound effects, it helps. A times D minus B times C. Now for the matrix we just did, we know that our determinant turned out to be 11 because that was the magic thing that we could factor out of the matrix when we were done. Well, if we had done the previous problem the fast way, and I had 2, 3, -1, 4, we would find the determinant of that matrix by doing 2 times 4 minus 3 times -1. And I go, sweet, that's 8 minus a negative, so 8 plus 3, that's 11. And then I would just write down the determinant matrix by saying A inverse is equal to 1 over 11 times, swap the diagonal, make the other numbers negative. And then you can decide whether to distribute the 1 over 11 back in or not. If the only thing you were asked to do in the question was to find the determinant and you were writing this by hand, if you were just asked to find the inverse and you were writing it by hand, I would probably quit there. But if it's a web work question, you're going to have to distribute the fraction in to make sure that you can answer it. So to put the fraction in, this would look like 4 over 11, -3 over 11, 1 over 11, 2 over 11. Our next vocabulary word here is that we say if a matrix has determinant equal to 0, that's a 0, not an O. But if her determinant is equal to 0, then it is not invertible. And the other word that we can give for not invertible, a synonym for that is to say that it is singular. So these two phrases are interchangeable, saying that a matrix is not invertible or saying that it is singular. So we can refer to this as a system of equations, but we can also take that system of equations and write it as a matrix equation. And the way that we would do that is to look at the left-hand side and think about writing this as some matrix times the vector x, y. And the result would give me the vector 5, 6. Just from the rules of matrix multiplication, I know that what has to be in here are essentially all the coefficients from up here. 2, 3, -1, 4. And you can check really quickly that when you do multiply these together, you get what we started with. So I'd have 2 times x plus 3 times y. Yep, that matches. And I'd have -1 times x plus 4 times y, which also matches what we have here. So one thing that we might be asked to do is to solve. Now, in general, just convention-wise, we often write these sorts of equations in the notation A times the vector x is equal to the vector b. So we talk about solving AX equals B kinds of equations. We already said, or I already said, that we don't have a way to divide by a matrix. But with our newfound skills, we do have a way to isolate the x by itself, because I know that if I take both sides of this equation and I multiply by A inverse, A times A inverse should give me the identity matrix back. And when I multiply the identity matrix by something else, it doesn't change the something else. So we can solve this system of equations by finding A inverse and multiplying it by the vector B. You might be asking yourself, why the heck are we doing that? We could have solved this in Algebra 2. We would have been done with it 3 minutes ago. You're not wrong. The reason we're doing this is because even though we aren't very good or fast at computing the inverse of a larger matrix, computers are great at it. So right now, we're just sort of building the idea of the skill. In the real world, computers are great at solving systems of linear equations, and we're going to let the computers do that work. In the context of 17b, we're going to practice and get the idea of it by doing smaller problems, meaning a 2 by 2 matrix that, yeah, we could have solved faster some other way. Conveniently, I gave us the same matrix back that we had before, which means I already know what A inverse is. If I want to solve for x, y, I know that I'm going to need to multiply A inverse by this B vector, 5, 6. And because we just did the problem, like multiple times, I know that A inverse works out to be 4/11ths, -3/11ths, +1/11ths, 2/11ths. Now I said the numbers were going to get messy, but that's okay. On your paper, I'll give us like 30 seconds to do this multiplication out. First of all, quick check. I've got a 2 by 2 times a 2 by 1. My inside dimensions match, so I'm allowed to do the multiplication, and my answer should be a 2 by 1. So this top piece here, I'm going to ignore the denominators. They're all 11. So I've got 4 times 5, which should be 20. -3 times 6 is -18. So 20 minus 18, I'm going to get 2/11. And for this piece down here, I've got 1 times 5 plus 2 times 6. So 2 times 6, that's 12, plus 5. So I've got 17/11. So it actually is pretty quick in terms of if we had solved that system of equations any other way, given that the numbers at the end are kind of gross, it's probably a toss-up in terms of time. So I would say now that x is equal to 2/11 and y is equal to 17/11. If I were to take this same equation, this ax equals b, but instead of putting a b there, put a 0, this is called the homogeneous equation. I don't know how to spell it. I'm going IOUS. There's probably an extra vowel somewhere, but I don't know which one to get rid of it. That's our homogeneous equation. And something really interesting happens when we try to follow this process of multiplying by the inverse to solve this thing. So if I multiply both sides by a inverse, whatever the matrix is, if I multiply it by 0, the result is 0, which means I get 0. Now you might be going, yeah, what can you multiply something by and get 0? You can definitely multiply it by 0 and get 0 back. But what's cool about linear algebra, there's another possibility. If you can find this A inverse term, right, if it exists, then the only solution is the trivial solution. But what if on this step, A inverse didn't actually exist? And if A inverse doesn't actually exist, it opens up the possibility that we actually have an infinite number of solutions to this equation. And that might not seem exciting now, but it will in the context of biology, because this solution means all the critters died. In general, I'm kind of hoping for a different outcome. And the only way that we get interesting biological outcomes is when A inverse doesn't exist. Let's talk about it. Yeah, let me erase some stuff. So let's say I've got the matrix 3, 2, 6, 4. Cool. I claim that this matrix, and just for fun, I'll call it A, but I claim that this matrix A is singular or non-invertible. And the way that I would show that is by calculating the determinant of A. Well, the determinant of A I would get by doing minus 3 times 4 minus 2 times 6. Now I have strategically chosen this matrix such that 12 minus 12 is equal to 0. Well, let's look at what that means in the context of this homogeneous equation. Well, if I take that matrix A and I think about A times X being equal to 0, then that would look like 3, 2, 6, 4 times XY is equal to 0. Well, if I multiply that out to form that system of equations, that says that 3x plus 2y is equal to 0, and 6x plus 4y is equal to 0. Someone clever might look at those two equations and say, but wait, that's not two equations. That's one equation in disguise. Because if I take the top equation and I multiply everything by 2, I get the bottom equation. Or to think about it graphically, this is really just the equation of a line if I rearranged it, right? If I take that top equation and I rearrange it to make it say y equals, I'd get 2y is equal to negative 3x, and I divide both sides by 2, and I'd get negative 3 halves x. Well, this bottom equation, if I also solved it for y, I'd have 4y is equal to negative 6x, so y is equal to negative 6 over 4x. And if we reduce our fractions, we get exactly the same equation. If we're solving a system of equations and it's two equations of lines, And graphically, what that means is we're finding the intersection point of the two lines. But what we just found is that these two lines weren't two lines at all. They were secretly the same line, which means there are an infinite number of intersection points. In fact, any point that falls on this line, y equals -3 halves x, any point that falls on that line is a solution. I promise it'll be more fun biology. But we kind of have to wait till tomorrow or maybe Friday to get there. For now, you just have to take my word for it. Interesting stuff happens when the matrix is not invertible. Boring stuff. All the critters died. Well, okay, that could also tell an interesting story, but sad endings where all the critters died. That's our only option if we're solving a homogeneous equation and we can find A inverse.